there are 3 slot machines. 2 of them are identical and one of them is a little crooked. This one is the one that's crooked. And you need to identify which one is this crooked slot machine as quickly as possible. So the rewards are Markovian. So here is the state space for the Markov processes that is executed by each of these slot machines. So that's S. And these slot machines have a transition probability matrix associated with them, associated with the Markov process. So it's P for this, so that's the normal one, and then one of them is abnormal, that's Q. Okay. And they issue rewards. This is x1, x2, etc. for the first process. This is x1, x2, etc. for the second slot machine, and this is for the third one. And of course, they obey the law corresponding to either P or Q, depending on whether it's odd or non-odd or normal. And let's assume that it's stationarized. Okay, so what we know here is that the learner knows that there are 2 of these slot machines which are the same. They have the same TPM, but the third one is different. But the learner doesn't know what the location of the third one is. The learner doesn't know what the parameters are either. Okay, so what are unknowns, I've captured them in this particular variable psi. The first one is the location of the odd arm or location of the odd machine. And then this P is the parameters or the transition probability matrix for the normal machine. And the Q is the transition probability matrix for the non-odd machine. The only thing that I know is that P is not equal to Q, but otherwise P and Q could be anything. And it could be any one of these 3. So that's the uncertainty in the L. So the unknowns are the location, the parameters of the normal arm, and the parameters of the odd arm. I will variously call this configuration because we will be given a particular problem instance where we will have to identify where the odd slot machine is. And so this particular set of unknowns, I will call them as a configuration for a particular problem instance, or the state of nature or ground truth. Okay. So what do we do to identify where the odd arm is or where the odd slot machine is? We pull the arms and then we observe the rewards. The important thing to note is that you observe the reward only on the arm that you're pulling. So even though they are issuing rewards, what you get is only when you pull that particular arm. And so we have actions and observations. So here is the first action that you took, which is maybe one of the arms, and then you observe a particular reward corresponding to that arm. And this goes on, maybe at the teeth time instant, you pull the arm AT and you observe that particular arm's teeth reward. Okay, so you do this until you get to a point where you decide to stop. You've gotten enough confidence as to where the odd one is, and then you'll have to declare that something is the odd one. So these are the actions and the observations. And our informal goal is to identify the location of the odd arm, which is L, as quickly as possible. And we would like to do this correctly with high probability. Okay. So applications abound, starting from visual search modeling. For example, images like these are supplied to you, and you will essentially have to identify which one is odd. So these are puzzles that you see, but these are also experiments that neuroscientists conduct, and that's what got us into this particular problem. In fact, it's trying to model one of those problems that we have to essentially look at the Markovian setting with a restless bandit, restless set of arms. There are also other examples: dynamic spectrum allocation, anomaly detection, etc. But my interest in this is not only these applications, but also from the decision theoretic perspective on the nature of the solutions that one gets in such settings. And I'll try to give a flavor for this at the end. Okay, so more formally, here's the history. History is all the things that you have seen or actions that you have taken up to a certain time t. I call that as HT. So actions, action, observation, action, observation, up to time t. Now, we also have this notion of a policy. So the policy is essentially a contingency plan forever into the future. So that's made up of pi 1, I call the policy pi. Pi is pi 1, your plan for time 1, pi 2, your plan for time 2, and so on. And what this does is it looks at the history at time t, it looks at the history up to time t minus 1, and then decides which arm to pull. So that's the AT. Alternatively, it could be a random decision. Pull a particular arm with this probability measure, which is lambda t on the set of arms. Or it could be something that says, I've gathered enough confidence, I'll now stop, and I'll declare L hat as the odd arm. Okay, so here's a little bit of notation. So let's recall what we mean by a configuration. It basically captures all the unknowns. Where is the odd arm? What are the parameters of the normal arm? And what are the parameters of the odd arm? Okay, so transition probability matrices. But then there is also this notion of a policy, and if you use a policy, your observations, your actions, etc., will follow a certain law. So that law I'm denoting as p pi, pi for the action and psi for the true state of nature. And if I take expectations, I'll use the notation e pi psi. Okay, so that's the notation. And so what we are interested in is how long do we take to stop our decision making procedure. So that's when you're ready with the decision. How long do you take to a decision? So that's this expectation, expected time to your decision. And then there is also this question about what's the quality of your decision. And the quality of your decision is measured in terms of what's the error. So you declare something as the odd machine. Is it correct? With what probability is it correct? So that's given by this. And what we would like to do is keep both of these low. Okay. And at this moment, without regard to this, let's look at policies which have low probability of error, and I'll call them as admissible policies, policies with low probability of error, and I'll call them as admissible policies, which are parameterized by this parameter epsilon. Okay, so this epsilon basically governs a bound on the probability of error. Its pi epsilon is the set of all policies pi, such that the probability of error given a particular ground state, psi, is less than or equal to epsilon. But it's not just for one psi. Your policy pi must be such that no matter what is the ground state, no matter what the problem instance is, your probability of error on this particular problem is less than or equal to epsilon. Okay. So that's the set of all good policies or admissible policies with a parameter epsilon. And our goal is essentially to find the asymptotics of this expected search time as epsilon goes down to 0. So I'm going to look at a limit as epsilon goes down to 0. But as epsilon goes down to 0, I anticipate that in order to be more and more confident, so that's what epsilon going down to 0 means, your probability of error must be smaller and smaller. I anticipate that in most non-degenerate problem instances, I have to wait longer and longer. And a little bit of thought and some familiarity with Wald's sequential probability ratio testing procedures will tell that this expected time to make a decision goes to infinity as log 1 over epsilon. And so what's the growth rate? That's what we are after. So to capture the growth rate, we basically normalize this by how it grows to infinity. And then try to look for policies which have the least growth rate. So in some sense, those are the policies that essentially try to minimize the rate at which these decision times go to infinity. So our goal is to find across all admissible policies with a particular epsilon, this minimum divided by log 1 over epsilon, and then we let epsilon go down to 0. So we want to find out this growth rate constant. Okay, so that's the question that we are interested in. Okay, so mostly I'm going to focus in this particular talk on the converse. That means no matter what policy, you're going to take at least this much amount of time. Okay. And so the way we'll do this, like most of the converses, is to use this second law of thermodynamics for information processing. And so what this particular data processing inequality says is that let's say that you have a random variable x and you're trying to distinguish between these two distributions. So this takes values in a particular alphabet, let's say A, and you have some distinguishing capability based on the x. So if x is distributed according to P1 versus if x is distributed according to P2, there is some distinguishing capability. That distinguishing capability, you could try to see what happens when you process the data and you get a particular y. P1 will induce a certain distribution Q1 on the other side after the processing, and P2 will induce a distribution Q2. So you can ask, how better is my distinguishing capability on the other side after the processing? And this second law of thermodynamics says that the processing capability is better here. You'll be able to distinguish things better here than on the other side. Okay, and this is where the D here stands for relative entropies. Okay, so now let's consider, we have a ground state which is the particular problem instance with an epsilon, with a psi. Okay, and we'll consider another problem instance, and the other problem instance is some other psi prime, with another odd location and parameters p prime and q prime, and that odd location is different from the odd location for the given problem instance. Okay, so let's take any admissible policy. Your admissible policy is something that must do well on the psi, which is your current problem instance, as well as on the psi prime. Okay, so that's what we'll do. So we'll think of these as two different probability distributions, and I'm going to tell how to do that. So for this x, let's take it to be all the things that we have seen, the history up to the time of stoppage and including the decision. So let's call that as the x. So that's the action, observation, all this up to the time when we stop and make a decision, including what's the decision that we have taken. And then on the other side, let's just take the output to be just the final decision. So let's write now, because you have a particular policy, I'm looking at a particular admissible policy. Because you have a policy, the law for this will be according to p pi psi when the true state of nature is psi. But if it is psi prime, the law for the same set of observations is going to be something different, that's p pi psi prime. And similarly, you get induced distributions on the other side, which will be q pi psi and q pi psi prime. The data processing inequality says that the relative entropy on this side is bigger than or equal to the relative entropy on the other side. So how do we use this? Okay, so the converse outline broadly goes as follows. Here's the data processing inequality. Now your policy is supposed to be able to distinguish between psi and psi prime. So that means that at the end of the exercise, when you make a decision, you're confident that your decision is correct, and that confidence is measured in terms of the probability of error being less than or equal to epsilon. That means that you've gotten a certain amount of, for lack of a better word to describe what you have gotten, I'll call it log of 1 over epsilon units of confidence in your decision. On the other hand, if it is so that you cannot get more than a certain number of units of this confidence per stage, so there is some sort of an information theoretic bottleneck, that means that your relative entropy cannot, if you stopped at this particular time, your relative entropy cannot be more than on the average this d star per unit time multiplied by the expected time that you have. So suppose this was true, then you can actually see that you must gain at least this much amount of confidence, but at each stage you are able to get at most d star, so you must wait long enough to be able to get to this particular level. And so that's data processing inequality, this bottleneck for obtaining confidence, which is coming from an information theoretic bottleneck, and then at least this much amount of confidence that you should get, that says that your expected time is at least this. So converses go like this, and the idea is to identify what this d star is. Okay? So that's telling you the growth rate of this expected search time. Okay. So now I'll elaborate on y log 1 over epsilon. It's quite standard, but it's quite illustrating as well. So I'll speak about why you actually get when you have a good policy this much amount of confidence, and I'll also tell something about this upper bound. Okay, that's the bottleneck issue. So let's now look at why a good policy gets log 1 over epsilon units of confidence. Okay, so for this we have to interpret what the q pi psi is. That's the q on the other side when the configuration is psi after you have done the processing, and this processing actually has thrown away everything else and it has kept only the decision. Okay. What this gives you is it's the probability of various decisions. What's the chance that you predict the odd one is the first arm, or the odd one is the second arm, or the odd one is the third arm, and so on. Okay, and so under your policy. So let's say that your configuration, let's say, is psi. The distribution then, because the ground truth is psi and your policy is pi, this is the distribution that will be induced based on the actions that have been taken. Now your policy is a good policy, the pi is a good policy. That means that you will put probability more than 1 minus epsilon on L, and in particular smaller than or equal to epsilon on L prime and all the others as well. So that's the nature of this distribution. On the other hand, under psi prime, your policy is good on psi prime as well. That means that on L in particular it puts mass less than or equal to epsilon, but on L prime it puts greater than or equal to 1 minus epsilon. And what this means is that you have essentially through your policy been able to skew the distribution one way when psi is true and another way when psi prime is true. how far apart these are is your sort of discrimination capability or amount of confidence that you've gathered. And this is approximately the relative entropy between a distribution that looks like this, which puts mass 1 minus epsilon here, and so on. And the other one skews it, puts 1 minus epsilon on L prime and epsilon on L. And when you do this, thank you. When you do this, you get the relative entropy to be equal to log 1 by epsilon. Okay, so that means you're getting this much amount of confidence. And so this relative entropy is equal to this. Okay, so that's, you've gotten this much amount of confidence. But what about the upper bound, the bottleneck? Per unit time, you can't get more than a certain amount. For this, just to illustrate the point, I'll actually go to a simpler problem, and the simpler problem is the one which is not the restless case, but the rested case. The rested case is where the arm doesn't move, the rewards don't move if you don't pull that arm. So that means that you're able to actually see the entire Markov sequence. Okay, so that's a simpler case, and let's see how to do this. And I apologize for the details that I'll put here, but I think it's important to indicate where the difficulty is when we move from the rested case to the restless case. So what happens in the rested case? So the rested case, you can write down the relative entropy. The relative entropy is just the expectation of the log of the likelihood ratio. And when you expand that likelihood, write it down as a product, and then take the logarithm, then it essentially breaks down like this. Some of the things to keep in mind are that this is the probability of seeing xt, some observation, given the history, so those are natural. But you have to bring in the actions as well. So what's the chance that you look at a particular arm or you pull a particular arm based on the history? That's given by your policy. I apologize, this should be, there should be a pi somewhere here. That pi determines the lambda. So this lambda comes actually from the pi. Okay. But the important point to note is that whether or not the ground state is psi or psi prime, for the history ht, your action is exactly the same. Okay, so that policy has been prescribed, and therefore the probability that you will take a particular action given this history is the same regardless of whether the ground truth is psi or the ground truth is psi prime. Okay, and when you write it out this way, you can see that the lambda t can be removed, and you can essentially write everything in terms of just conditioned on the actions. So that's an important point to keep in mind. And when you do this, you will essentially get, you can reorder this in the rested case, and you can essentially see that what's the chance that whenever I pull this particular arm, and maybe I have pulled it a certain number of times, let's say na of tau until the time of stoppage, what's the chance of seeing a particular sequence, and I can write that in this particular product of probabilities for the rested Markov setting. And similarly in the case when things are coming from the alternate configuration, which is the psi prime. When you do this, you will essentially get to see that there is some sort of averaging that could be leveraged now. Some law of large numbers kicks in, because when epsilon goes down to 0, you have to wait longer and longer and longer, and therefore you get to see many samples, many pullings of a particular arm. And when you do that, then law of large numbers indicates that the number of times you observe a particular state for a particular arm is going to be roughly the equilibrium distribution, which is the stationary distribution or the invariant measure for this Markov process. And also the transitions occur in exactly what is prescribed, at least on the average, what is prescribed by the transition probability matrices. And therefore, you can essentially write this, you can turn it into expectations, and those expectations will involve expectations of log of the likelihoods corresponding to rows from the transition probability matrix P and Q, and then averaged. But the averaging will be with respect to the empirical measure of observations, but the empirical measure of observations in this particular case will be the stationary distribution of the Markov process. And so you will get a relative and average relative entropy averaged with respect to the invariant measure associated with this arm. And of course, there is the number of times that you pull this arm that comes in. And in order to justify the step from here to here, in the IID case, there is something called Wald's lemma that you could use. In the Markovian case, you need to use an analog that can be established, and that I call that as the Wald analog. And that gives you a sort of what's the expected number of times a particular arm has been pulled and how much information or confidence you're able to extract per unit time. And so you see how relative entropy enters into the picture. And now what we do is recognize that when I sum this up, it's actually equal to the stopping time, and because there is an expectation, it will be equal to the expected stopping time. So I can multiply and divide by that, and I'll get a probability measure here, which is sort of a proxy for the empirical measure. And once you see that probability measure enter in, you can take the supremum across all possible probability measures for actions, and that gives you an upper bound. And so that tells you that the relative entropy, which is the relative entropy on the left side of this second law of thermodynamics for information processing, that one is upper bounded by an expected amount of time that you will take for a decision, multiplied by this is the upper bound. Per unit time, you don't get more than this much amount of information or this much amount of confidence. So this one is asymptotic as epsilon goes to 0, and in the IID case it is not, it's exact. But in the Markovian case, it's asymptotic because you will essentially have, I've replaced the empirical measure with the stationary measure. So this is asymptotic, and then this of course is asymptotic. This is an upper bound. Okay. All right, so that tells you where you get the bottleneck from, and so there's one more point to keep in mind. Your policy is something that's able to distinguish any two states of nature which have the odd arms at different locations, and so this psi prime is actually arbitrary. And if your policy is a good policy, it must be good no matter what this psi prime is, which means, or you can interpret it as an adversary choosing a particular psi prime that's toughest for you to distinguish when the ground state is psi. And therefore, you should be able to work even in that particular case. And therefore, what one can arrive at is like there is an adversary who chooses a psi prime with the odd arm being at a different location compared to yours. He also has the flexibility to choose the parameters in whichever way he wants, so long as the p prime is different from q prime, and you should be able to cover for that. Okay, so that's the interpretation of this particular information bottleneck. Okay, so with this you essentially get the lower bound, and this is for the rested case. So what happens in the restless case? Okay, so this is just a summarization. Upper bound on the relative entropy on the left side actually yields a lower bound on the expected search time. So since this d star is the per unit time upper bound, you need to wait at least how much you need to get divided by what you can get per unit time, and so you need to wait at least this long. Okay. Yes.
So is this 0?
What is 0?
Is the whole quantity, because like p and q can be arbitrarily close together.
Yes. So P and Q can be arbitrarily close together, but P and Q are different, and in this particular problem, so this is the problem where you are essentially looking at, there are two arms of one variety and the third one which is different. You could be very close to each other, but they are still different, and that's the odd arm, and therefore the answer is not 0. It can be arbitrarily close to 0, but
are you
for
thinking of P and Q as fixed, or is the inf also optimizing over?
Yes, the inf is actually optimizing over P and Q as well, and there is positive separation for this particular problem. And the positive separation is because, maybe can I answer this at the end? Yeah. So yes, I'm looking at inf across all possible P and Q, but P and Q must be different. And given a particular problem instance, if you look at the alternatives and look at what the relative entropy between those two are, there is positive separation. The positive separation though depends on the parameter. So it could be closer and closer to 0, which means you might have to wait longer and longer. But I have answered the question as well. Okay.
So the rewards that you get have some assumption on the distribution?
So I don't think of them as rewards. I think of them as observations that enable you to distinguish. But yes, they depend on the parameters P and Q. So did I answer your question? They come from P and Q, right? The transition probability matrices are given. Okay. P and Q again can be arbitrary, but P and Q cannot be the same. Yeah. Okay, so now I'll. So are there any other questions? Because I'm going to jump to the restless case, and this is a good point to pause and answer questions. Yes.
Is this computable?
Which one? This D star? In the restless, in the rested case, yes. In the rested case, well, it's an optimization problem. In certain explicit, like for example, IID case, it is computable. In the Markovian case, rested Markovian case, that's this particular situation. It depends on what your definition of computable is. So I think numerically you can compute. Okay,
Rajesh?
so any other questions?
Yeah, I feel that the, Rajesh, I feel the real issue in the earlier stream of questioning was in the notion of an admissible policy. So if you allow P and Q to get arbitrarily close to each other, it's hard to imagine how you could construct a policy that with positive probability finds the correct location of the bad arm.
So the reason you're able to do that is that the nearest alternative to a particular case is something which has positive distance. And that positive distance comes from, so here, so imagine the following. So let's go back to, the picture is a good thing to have, although I have to move back. So let's look at this. So this is P, P and Q. So let's look at what the nearest alternative looks like. And then if there is positive separation, I think that will answer the question. So let's say the alternative is here, and I can have any P prime and Q prime. So let's see what's the best Q. I'll give you the answer as to what the best Q prime is. So the Q prime, that is the odd arms distribution, should equal P in that case. One can solve this problem and demonstrate that that's the case. But the nearest alternative P prime is a convex combination of the P and the Q. Because I need to force the P and the, I need to force the transition probability matrices of this and this to be the same. And so it's a convex combination of the P and the Q. And if P and Q are different, the convex combination is different from the new Q prime, which is actually equal to P. And so this forces a positive separation.
If you go a few slides ahead, you had a definition of what it means for a policy to be admissible for a fixed epsilon.
Yes, here.
Yeah, so if you look at, you might ask yourself, is there a policy pi that actually has this property for all pairs P and Q? It seems hard to believe that there would be such a policy if P was allowed to be arbitrarily close to Q.
That is correct.
So somehow the answer doesn't quite address this issue, I think.
So that question is a valid question. So upfront, it is not clear that there is a policy that actually meets this, no matter what psi you have. But I think in this particular case, there is an answer to this question that the set is non-empty. In fact, there is a demonstration of a particular policy. I must say not for the restless case, but for the rested case. And the reason is because you might take longer on that. The nearest alternative is positively separated, but maybe quite close. And you'll have to essentially wait as long as that relative entropy, 1 divided by that might be small, but it's positive, and therefore it depends on the psi. And the point to note perhaps is that when you look at, when I go and solve this infimum problem, the question is there so I think your worry and also your worry is that this infimum, because I have arbitrary parameters P and Q, I might be very close to my true configuration. But for a particular configuration where P is not equal to Q, there is positive separation. And therefore, this is actually a positive quantity.
Okay, I think you've answered the question. Thank you.
Thank you. So let's now get to the restless case. How much time do I have? 2 minutes. Okay, so quickly in the restless case. Okay, so in the restless case, I'll just tell you what goes away and then what one needs to do. So here was the so the first step is of course something that's valid, but the second step where we exploited the rested nature, that's no longer valid. But what you can do is something that we actually did use, but we exploited that in the specific rested setting, but you'll have to go back to the restless setting and employ it. And that's essentially writing this particular expectation in terms of state action occupancy measure and an associated expectation. But this time, the state and the action the state should take into account the delay. How long before did you play this particular arm? Because that will determine what observation that will determine the law of the observation that you're going to get when you actually pull that arm. And so you have to essentially write it out in this particular fashion. And when you do this, there is a natural bottleneck that you can write down, and this bottleneck now is in terms of supremizing the state occupancy measure. But because these relative entropy terms depend only on the marginals, that is how much delay for a particular action, for a particular arm, and what observation did I see last for that, there is a natural temptation to write this completely in terms of the marginals. But when you write it in terms of the marginals, it's not clear that once you do this supremization and you capture the nu, that when you're trying to come up with an achievable rate, you'll be able to do that. And so this particular step essentially gives you an upper bound that could potentially be loose. And what one needs to do is tighten this upper bound in some way. There are some observations that one can get. For example, I'll just write down one particular condition that one has. I don't have time to go over this in detail, but that's the occupancy measure essentially satisfies this particular property that the expected delay to pull an arm, okay, is actually equal to the inverse of the frequency with which that particular arm is pulled. And that's a constraint that one can impose, and somehow one must essentially optimize the D with these constraints and get a tight bound. That's something that we would like to overcome if possible, and there's a natural way to overcome it. The natural way to overcome it is to enlarge your state space, to keep track of all the delays and all the past observations, and view and write down the optimization in terms of an occupancy measure for that particular enlarged state space. And it's this which there is a problem with computation, because now the moment you essentially allow yourself to have any possible delays and any possible observations, then this becomes a countable state space, and then solving this optimization problem becomes a bit of a difficulty. So there's a program that one can come up with that will essentially achieve this upper bound or lower bound in terms of the expected search time. Maybe we can discuss this offline. And I'll just say that we have been able to match the upper and the lower bounds. The lower bound, upper bound on the D comes from here, but then you'll be able to make policies that meet it in the case when things are IID, when things are rested Markov. And additionally, when you essentially have the restless case, situations when you want to pull a particular arm, but your hand is trembling, and with some probability you pick something that is at random. And whenever you have this trembling hand phenomenon, analysis becomes easy. So there's some regularization that happens. And in these cases, we have been able to resolve the problem. Okay. So what's in progress is the case of steady hand and unknown PQ. And this is also for the case when P and Q is known. So to summarize, here's the theorem. For learning to detect the odd restless Markov arm, the lower bound is given by this 1 over d star xi, taking into account the state occupancy frequency. Thank you.
So, since we had questions, maybe we can take it over T, which is waiting for us. We are running 25 minutes late. So we'll come back at 3:35. Don't let Rajesh go. Do ask him questions, but let's do that over T.